falling apart in here because of the humidity again, but I said I'm popping the door open because that dehumidifier is not doing it. So I did get some stuff on D2L finally. What's on there right now is basically the stuff I went over last time. So I'm still kind of missing everything from the previous chapter that we spent so much time on. What chapter is that? Well, 4.2 we spent a lot of time on. That was the, what do you call it? The redox reactions. So I still got to get that on there. I guess there's a little more from there. But so there's something you can start practicing is what I'm saying. I'm going to move on to chapter 5 to do the energy stuff here. I did upload a PowerPoint. I'm going to just follow my PowerPoint. But at least let me point you to table 5.1, the specific heats. So I'm going to talk about those today. Realize I'll give you these values on a test, so you don't have to memorize them, but I'll show you how they work. Specific heat. I guess I should say this. We measure heat in joules. I think that's all you need to know for now. We use capital letter J for it. So a measurement of energy heat. Specific heat is the amount of heat required to raise 1 gram of a substance 1 degree C. So if you, whatever it is, and think of it as something pure for our cases, but something like, doesn't matter what it is, whether it's water or some other liquid, or a solid or a metal or whatever. If you have 1 gram of it, and you want to say take it from 20 degrees to 21 degrees C, the amount of heat that you have to put into it to make that happen. It actually works out that backwards as well. That's exactly how much heat you have to take out of it. If you have 1 gram and you want it to go down 1 degree C, it's the exact same amount of heat it takes to bring it up 1 degree C. So that's what specific heat is. And the units for it, degrees C, I'll put like that. But usually I just go J, G, degree C. When there's 2 units together, we put a dot there. And for water, it's joules per gram per degree C. Usually when you see this written, you'll see 4.184 J, G, degree C. like that. But just like when I always tell you guys, if you have grams per mole, I always tell you to be more formal and go 14.01 grams over 1 mole. A 1 goes with the mole. You see it written like this a lot, but I would tell you to go ahead and go 4.184 joules to 1 gram to 1 degree C. So there's an implied 1 here for these as well. With me so far? Okay. And the way this is usually depicted is we use, Q is just a symbol we use for the heat transfer. M equals mass, that is grams in the units we'll use. And we use a delta T for the degree C, because that really means temperature final minus temperature initial. Whenever you see a delta in science, delta, it's the capital D in the Greek language. I think it's Greek or Latin. I think it's Greek. It's always final minus initial. If you went downtown with $20 and you came back with $15, your delta money would be negative $5, right? If you left with 20 and you came back with 15. If you left with 20 and came back with 25, you would think of your delta money as plus 5, right? $20. And then final, later when you come back, you have $15. You want that to be a negative 5. That's why you go temperature, I should have said money. I'll do this. Your money initial is $20, your money final is 15. So if you wanted to do a delta, if I did final 15 minus initial 20, there, I'll get a negative 5. But if it was, your initial was 20, but your final was 25, you want this to be plus 5. Again, I'm going to do final minus initial. 25 minus 20 equals 5, that is positive 5. So that's just my way of saying this is why it's always final minus initial and not the other way around. Because that makes it the intuitive thing that you would think it would be. If you're down $5, you want your delta money to be negative 5. If you're up $5, you want your delta money to be plus 5. So that's why when we do temperature, we'll have an initial temperature and a final temperature, but this is always how you calculate the delta T, and then you'll get the sign correct on it. So in practice, we're not dealing in money, we're dealing in heat, energy, joules. Most textbooks write it this way, the amount of heat equals the symbol we use for this, is almost always C, and I frequently use CP for the specific heat at constant pressure. I don't think your book bothers with the P, but I can't help myself, I want to use the P. So it's CP times the mass times delta T. So let me put it like this. Let me go ahead and jump to one of these problems. I did example 5.1. 8.0 times 10 to the 2 grams of water the initial temperature says the temperature of the water increases from 21 degrees C to, and I'll go ahead and label them as final and initial, to 85 degrees C. How much heat did this take? So you just use this formula. But, so you have this, the mass. In this case, I'm going to write that as 800 grams, even though it's only two significant figures, just to make this look more simple. Your delta T here, so calculate out in the margin, your delta T is 85 minus 21, what is that? That's 64. So you got degrees C, you got grams. If you look up on this chart, so like I said, you don't have to memorize it. For water, it's 4.184. I erased it already. Like this. Joules per gram per degree C. You multiply all those together, it tells you how much heat. If I'm a little more formal, I would go 4.184 joules, and down here I would go 1 gram, 1 degree C, and over 1, 800 grams, and over 1, 64 degrees C. And I like doing it that way just because you can see that grams cancel, degrees C cancel, we end up with joules, which is what we want. This was really two significant figures. Scientific. .184 times 800 times 64. I get 52.3 joules. That's all there is to it. Is that really what I got? Is this nowhere near what we think back here? Did I do that right? 4.184 times 800 times 64. Yeah, I calculated that completely wrong somehow. My calculator says, but I'm keeping two significant figures. The 4 does not round to 1, so I've got really got 2, 1, 0, 0, 0, 0. I'm not doing more than that. This is frequently a good point where you can use kilojoules. So that means joules. I only want two significant figures. I'm going to say 210 kilojoules. And yeah, I guess since it's two significant, no, I guess that's fine because I don't have to put I don't have a decimal there. So that's showing two significant. That's fine. They have on there times 10 to the 2 kilojoules. Either one of those is correct. Kilojoules. Okay, you guys follow that? It's not hard, right? You good? Check your much heat does it take iron 502 grams of iron C to 250 degrees C. And C, E for iron equals, look on the chart, so you need this, or at least a chart where you can look it up. Can you calculate that? Somebody calculate that. Q is what we're looking for. How much heat in joules equals C times the mass in grams times the delta T. Anybody calculate that? Same thing I just did. $50,114?
Yes, not 50,714.
Yeah, well, that's what we got. So if I calculate this, just trying to do a little group participation.
What would you look at to see if it's just the
My calculator, hold on a second, says 50. What'd you ask me?
how do you know when you see if the dollars number or the numbers?
Okay, nothing after the decimal, nothing after the decimal. I think this is probably showing two significant figures maybe, but I would picture it like that really. They do this a lot with temperature. Nothing after the decimal. Since this is addition subtraction, we would just do this with nothing after the decimal, so that's three significant figures. You give us this one in 3, and this one in 3. So 3 significant figures is these. The 1 does not round to 7, so I'll go 5, 0, 7, 0, 0. Joules. And that's fine the way it is, because I'm not putting a decimal there, and it's showing 3 significant figures. In the book, they've got this. They've got this. 5.07 times 10 to the 4. So one of those. Or you could write kilojoules, that'd be correct too. So that, or that, either one of those would be correct. I know that's loud, but I'm in here sweating without that door being open, so I don't know what else to do. Okay, two examples like that. What's the other one? Okay, variations on this. Example. Example. Two. Paraphrase this. So 348 grams of an unknown metal. Words. Uh, 22.4 degrees C to well, this time we're asked to calculate the specific heat. You can use the same formula and use a little bit of algebra. Q is the heat flow, that's in joules, equals Cp, which is what we're looking for, times the mass, times the delta T. So the 6.64 kilojoules, that's this. Since the Cp is going to be in joules, I guess you could report it in kilojoules, but we're going to look on this chart and see if it's there. So everything on this chart is in joules per gram per degree C. So maybe I want to do this. For the left side, you see what I mean? So that gets this side in joules. Cp is what we're looking for. The mass was 348 grams. Over here, I'm going to say delta ET equals TF minus T initial. So delta T equals, the final was 436. That is 43.6. So what is that? You do that in your head?
Sure.
Did you? I sometimes can, and sometimes I just can't. So. All right. So if it is 21 point, and you're solving for this, I guess if I rearrange that, I would go kilojoule, and then 1 over 48 grams, 2 degrees C equals CP. So I just divide both sides by these two things. Divide this side by 348 and divide this side by 21.2. That's what these are. And then you solve for CP. You'll notice kilojoules cancels and you're left in joules per gram degree C. Joules per gram degree C. Let's see what we get. Times 1,000 divided by 348 divided by 21.2. I get I've got a few more digits here, but I know we don't need them. This is metric to metric, so those both are both exact. My little one there is exact. These ones are exact. So I've got three significant figures, 3 and 3, so I'm keeping those 3. So that would be an acceptable answer. They didn't do it in scientific notation. I wonder if we can figure out what metal it is. I'm looking for something that's close to 0.9 on here as a metal. I don't see a metal on there that's that, but maybe they didn't mean for it to be so specific. Specific heat of aluminum? I don't see it. Oh, 0.897 is aluminum, so I guess we could assume that's probably aluminum. Specific heat really isn't enough to identify a metal because some metals are very similar. Okay, you understand that one? You understand the algebra? U4.5. Okay, this is the check your learning part of this one. Uh, 1.43. The grams are 217. So what's 39.1 minus 24.5? 14.6. All right, somebody do it with me. Times 1,000 divided by 2, 17, 6. I get 3, 3, 3 significant figures. Joules per gram per degree C. Was that one in kilojoules? Yeah. Let's get that. Totally the same idea though. Example 5.3. Page 90. Was looking at the wrong one. 360.0 gram. They say piece of rebar and they say steel. And then further down they say, what they say in the solution. Anyway, they tell you use the specific heat of iron. Yeah. The specific heat of steel is approximately the same as iron. So let's just say iron. Into C. So the water is at 24.0 degrees C. Final temperature of the water is 42.7 degrees C. Assume the CP for the metal, I'll say so assume the CP is that of iron, and if I look here for iron is 449 joules per C. Okay. This one is slightly different, but think of it like this. The amount of heat that flows out of the metal equals the negative amount of heat that flowed into the water. Maybe it's easier to think of this side as negative, but you drop the iron into the water. The water goes from 24 degrees to 42.7 degrees. So was the iron hotter than the water or colder than the water? If putting iron in the water made the water temperature go up, so you drop a chunk of iron in here, and it makes the temperature of the water go up. Do you see that? That tells you iron is hotter than the water. Heat comes out of the iron. So it might be easier to think of it like that. The negative amount of heat that came out of the metal all goes into the water. That's a comma. Does that make sense? The amount of heat lost by the metal is equal to the amount of heat gained by the water. Does that make sense? Okay. They have the negative sign on the water, but it won't matter which way you do it. All right. CP, I'm going to go CPM for the heat capacity of the metal times the mass of the metal times the delta T of the metal equals, got that out of proportion, the CP of water times the mass of the water times the delta T of the water. Does that make sense? Okay, here's what I know. Let's go ahead and do delta T is T final minus T initial in the equation times the mass of the water times the CP of the water. And then let's do T final. Is T final for the water minus T initial for the water. Let's make this T final for the metal minus T initial for the metal. Mass of the metal, that way. And I'm just going to write CPM because that's what we're trying to find.
I think we're assuming
There's one more thing also assuming. There's 1 gram. That's important because we weren't given the grams of the water. We were given the milliliters of the water. So we need to find how many grams that is. I think on a test, I'd just be more straightforward and tell you how many grams of water. We'll do a lab similar to this. We're just going to weigh the water. It's easy enough to weigh. Okay, so let's find out the mass of the water. 425 grams. I'll just say W. The density is 1.0 grams of W to 1 milliliter of W. Milliliters of water. I'm just doing this to make our units cancel. 1 milliliters of water, 4.3 grams of water. It's really 1/1, so we end up with 425 grams. Density of water changes a little bit with temperature. I think that's only true at 20 degrees C, but I guess it's negligible enough in this temperature range. But all right, so 425 grams of water. All right. And it's an unknown metal. Is it unknown? Oh no, it's a known metal, okay. That's not what we're looking for. CP is not what we're looking for. Final temperature, we're looking for that. That's what we're looking for, final temperature of the metal. Okay, CP of water, 4.184 joules per gram per degree C. I got that off the chart. It's one of the few things I memorized in the world. And iron was 0.449. Joules per gram per degree C. The mass of the iron 360.0 grams. Okay. Initial temperature of the water, final temperature of the water. So 42.7 for final. Degree C. Initial for the water, 24.0 degrees C. Okay. So far everything is kind of straightforward. Of course, we had to calculate the grams of water. Everything else is given to us. We just fill it in. I got this from the chart, and yeah, this is on the chart too. So all of this is given. Here's the thing. When all the heat transfer is done, you also assume that after that happens, and all the heat has come out, and this is 42.7, the water is 42.7 degrees. These are in equilibrium now. If the heat has stopped flowing, they're both in equilibrium with each other, meaning the iron final temperature is also 42.7. That's kind of the trick here. You see what I'm saying? Once all the heat is finished flowing out of the metal to the water, and it stops flowing, and we don't see the temperature changing anymore, we go, okay, we're done, our experiment's done, the final temperature is 42.7, it just stays there. Typically, you would do this in what we call a calorimeter, so heat can't escape this chamber. So when it finally stops, so what I'm saying is, this final temperature for the metal, equals temperature final for the water. So I'm going to write 42.7 here. Degrees. Do you follow that? So now we're down to one variable, and the rest is just a bunch of painful algebra. If it were me, I would divide both sides by this and this. That'll cancel, so. Those units are going to cancel. 360.0. Those units will cancel. And I'll leave it like that. I could also say, no, let's not do that yet. Let's get a numerical value for this. No, I'll do it more fancy. If you want to get fancy and put all the algebra together, the first thing I would do over here is swap these two. I would go temperature initial for the metal, negative temperature initial for the metal. You see what I did there for algebra? I'm just being fancy here. We could have got a numerical value here, and then subtracted 42.7 from it, and then multiplied both sides by -1. But this is plus 42.7 minus temperature initial. Instead of doing that, I went minus temperature initial plus 42.7. That makes this look a little cleaner. Now I'm going to subtract 42.7 from both sides. Minus 42.7. And I'm down to there. Negative temperature initial equals all of that. You still with me? You can do your algebra different if you want. But I had plus 42.7 here. So I just subtracted 42.7 from both sides to show you how fancy I can get with algebra. I think one more thing I'm going to do, as long as I'm being fancy, is I'm going to multiply both sides by -1, which makes that positive. That'll make that negative, and that positive. Am I driving you crazy? You can do your algebra however you want to. I just want to do it all in one shot in my calculator. As long as you can get it set up correctly to begin with, you can solve for it. What else should I do? As long as I'm being fancy. Equals. I'm going to swap these two. 42.7 degrees C minus all of this. After all this, I'm going to end up with the wrong answer. That's what I get for trying to be fancy. And then what? There. So all I've done is swap this term with this term. I just switched them around. All right, now let's crunch through all this. See what you get for all of that. The delta T, 42.7 minus 24.0. We really have to do that first. I get 18 degrees C. 18.7 degrees C. And now I can go, this is what I wanted, 4.184 times 425 times 18.7 divided by 0.449 divided by 360.0. Definitely done something wrong. That's what I got. Negative, what'd you get? I got something huge too. You shouldn't have. That's what I get for being fancy. What should we do? Should we go back? Playing around, it was 0.449 joules per gram degree C. 360 grams. Final temperature was 22.7 minus initial for the metal. And then we're screwing around. 4.184 times 425 times, and what was this? 18.7, is that right?
Yep, 18.7.
So let's do it like this. 4.184 times 425 times 18.7. Grams cancel, degrees C cancel. What we've got is joules. That's how many joules went into the water from the metal. Truthfully, 433, we really should go joules. All right, over here, this is what I wanted to avoid. Because now we have to distribute on both sides. But I'm feeling better about this. So 0.449 times 360, I get 3 and 4, so let's go with, I feel like we should keep an extra digit. Whatever. I get 162 for that. grams cancel, so I have joules per degree C. And now we have to distribute it. All right, whatever. 162 times 42.7. This is 42.7 degrees C. So if I multiply this and this,
Yeah.
say again, I multiply this by this, and then I multiply this to this. It's like, for this, I can go AB plus BC.
Okay.
So that's what I'm doing. So the first term I'm getting, you know, I'm going to make sure. Three significant figures. So I get the degree C cancels, so I get joules. Yeah, that's right. And then minus 162 joules degree C. This is going to be degree C. So this will be in joules. So 162 times this is 162 temperature initial of the metal. Maybe I like the other way better. Anybody see a better way to do the algebra? I know I set it up right.
Well, then we keep going.
Huh?
Subtract.
The next thing to do is, yeah, we'll subtract this from both sides, and then the last step is we're going to have to divide. All right, so 33200 minus 6920. So subtract this from both sides. They're both in joules, so that's correct. I get 280, and I guess nothing after the decimal, nothing after the decimal. I think we have to keep all of those. So one of the reasons I wanted all the algebra done all at once because of significant figures. Let's see. The last thing to do is divide by negative 162. I still feel like something's wrong. .184 times 425. 18.7. That's right. We divide that by 162. My problem is we're going to end up with a negative value, but we shouldn't. Okay, I know anything we should do. Let's just call this delta T of the metal for now. Degree C. I'm spoiled to using spreadsheets, you can tell. So instead of leaving that as subtraction, I'm going to do it like this, the delta T of the metal. So let's pretend we didn't bother with this yet. We just have delta T of the metal. I'd like if it came out to what the book got. And now we can just divide both sides by this. And let's not round this yet. Let's keep 33.252. 33, comma 252 divided by 162 leave that at 205. When we divide, the joules go away, so we're in degrees C. Okay. I think that's the best way to do this, because now we're just going to go temperature final minus temperature initial for the metal. Temperature final minus temperature initial for the metal is 205 degrees C. Temperature final of the metal was 42.7. Okay, this feels a lot better. Okay. Subtract that from both sides. Final minus, I still get a negative temperature. Oh, it's this negative. I forgot this negative at the beginning. That negative, this is all times a negative. This is all times negative 1, times that. Negative 1 times that. Okay. So if I distribute that through this, I get negative here, positive here. Okay, good. So I'm adding 42.7 to both sides. You with me? Do y'all like watching me do math in class? Okay, 205 plus 42.7. So we're adding instead of subtracting. I get 247.7. I don't think those. So initial temperature with the metal should be somewhere around that. Degrees C. They had 248 degrees C. Okay. I'll buy that. 0.7. Yeah. Addition, subtraction rule, we had 205 here. And then we added 42.7. This has 1 after the decimal. This has 0 after the decimal. So we were supposed to keep those. So 248 degrees C. And that's exactly what they have.
Would you make negative all there?
Yeah, it was this negative that I forgot. So this whole side should have had a negative out here. This whole side should still have times 10 to the times negative 1 here, times negative 1 to all this, times negative 1 to this. And then once I split this out into the components, I did negative 1 times the 42.7. It was some space. It was negative 1 times delta T. And then when I split the delta T out into 42.7 minus temperature initial, and then I went negative 1 times this, negative 1 times this. So negative 1 times this was negative 42.7. And negative 1 times negative Ti gave us a positive Ti. And that's why I added 42.7 to both sides to make that go away. And then we ended up with a positive. Does that make sense? There's no way around all the algebra. I think that was the smartest thing to do, is to leave that as delta T and then break it out later towards the end. We were way off track before I did that. And we landed on exactly the right answer. $248 gram piece of copper is chopped into 390 milliliters of water 26. Degree C. The final temperature of the water was 39. 9 degrees C. Calculate the initial temperature of the water. Copper on this chart is 3. All right, try it. Make yourself see it. Anybody print this out? Are you looking at it online? So you're looking straight at the answer anyway. You want to go through it? You should be giving it. Please don't do that again. Yeah. I will put one like that on the test. So practice your algebra.
You will put them like that on the test?
Yeah. Just one. Should I put 2 or 3?
The basics.
This one is very similar, so yeah, let's just go on to this one. That was, this I set up was to check your learning for 5.3. I think in this lab we'll identify an unknown metal, or trying to. Let's see. 59.7. Gram is submerged in boiling water and transferred quickly to 60 milliliters of water. This one is slightly different. 60, 0. From a boiling water bath. Wow, that's terrible. That's fire. There's the chunk of metal. Here's a bunch of fire. This is boiling water. Over here is 60 milliliters of water. So you transfer it from the boiling water and you drop it over here into 60 milliliters of water. That is at 22.0 degrees C. Okay. Final temperature of the water. Final temperature of the water is 0. Okay, follow me here, just to suss out a little more info. What temperature does water boil at? You happen to know? 212. Huh? 212. Fahrenheit. What degree C? It's 100. The degree C scale is scaled for water. So it freezes at 0 and it boils at 100, and that's literally how the scale was created. They said, here's the here's my mercury tube down in frozen, and then I heat it up, and it gets to 100 degrees, so the mercury rises, so I make a mark down there. As soon as it starts boiling, I make a mark, and then I just divide it 100 times. That's literally how Mr. Celsius did it. That's what the Celsius scale is. It's based on water. So boiling water, degree C. All right, so let me ask you this. And let's not forget our negative sign this time. Negative all of that. Okay. There's okay, what's the initial temperature of the water? Temperature initial for water. Yeah, I didn't want to. It's 22.0. 22.0 degrees. What's the initial temperature of the metal? This is the initial, 100 degrees. You just assume it's been in there long enough to come to the same temperature as the boiling water. And then you move it as quick as you can and drop it down in there. So, initial temperature of the metal, 100 degrees C. I'm going to assume there's a decimal there. Okay. What's the final temperature of the water? 28.5. And what's the final temperature of the metal? You infer this. Huh? That was the initial. If you put it in 60 degrees, that would be a delta. Yeah. So you put it in here, you wait a while until the temperature stops changing. Assume this is perfectly insulating so no heat can get out anywhere. Put the top on it. So when the temperature stops rising at 28.5, you assume the metal and the water are at the same temperature. We'll do a lab like this, so it's good to go through this now. So we're going to assume a very good assumption, that's 20. So those values we actually have both of our delta T's. We can go ahead and calculate them. The mass of the water, if we're still assuming the same density, this would be a little more straightforward if they just gave you grams of water instead of milliliters. Right, but we'll do that. So 60 grams of water, so we have this. We have the grams of the metal. We have this. The CP of water we can just look up on the chart. And since this is copper, what am I reading? 5.4. Oh, I didn't erase this. So it literally says unknown metal. It didn't say copper. Example 5.4. So this is what we're looking for now. It's an unknown metal. This is the only variable we have, the CP of the metal. This is a lot easier because we have our delta T's. What's the delta T for water? Final minus initial. Final temperature of water minus initial temperature of water. So 28.5 minus 22.0, what do you get? Sorry, what is it? 6.5. One after the decimal, one after the decimal. So we actually reduced down to two significant figures. Degree C. Mass of the water, 16.0 grams. And we use 4.184 joules, gram, degree C equals. What's the delta T of the metal? initial minus final. Excellent. You said negative. Yep, it's final minus initial. It's 28.5 minus 100. So the delta T of the metal is negative. What is it?
Negative 70.5.
Mass of the metal, 59.7. And I'm just going to write CP, because that's what we're looking for. And let's not forget -1 times all of that. We could go ahead and do -1 times this just to get rid of the negative. I don't have to distribute it. All I got to do is move this -1 to the inside of the parentheses and I can get rid of this negative. You see that? Algebra-wise? Huh? Well, I could put the negative here, but then ultimately I'm going to do a negative times a negative, that's going to become positive anyway. So I'm saying let's just go ahead and take this -1, apply it here, and then we're done with the negative. See what I'm saying? Does that lose anybody? It's a simple algebra step. It just might look deceptive. You see what I'm doing? I'm going to take this -1 and move it inside the parentheses. But the one of these that I'm going to apply it to is this one. Should I wait? Would that be less confusing? Okay, let's leave it there. So we can go ahead and get a numerical value over here. So multiply these things together. We're going to end up in joules. Grams and degrees C are going to cancel. And I say we keep a few digits. 4.184 times 60. 0 times 6.5. Let's just keep those digits for now. And we can go ahead and multiply these things together. 59.7 times -71.5. So just these two give us -426.855. Times CP, so I'm bringing that down. Still, all of that needs to be times -1. You with me? Okay. I could write this part. This is just better on my eyes, because it looks more like algebra. You okay with that? I'm getting rid of this bracket, and I'm just writing the CP on this side. Same way we write 10x equals 12 or something. You usually don't put the variable in the front. It also doesn't get in the way of the negative. You okay with that step? I just neatened this up a little bit.
Maybe put like a time for the CP in there.
Okay.
That would make it work.
And I still have I better deal with these units. This was grams. So this is actually, this times this is -4, 2, 6, 8, 5, 5. And I have to go with grams degrees C. G dot degrees C, that's the units. I've got there G degrees C, forget this. Combining G and degrees C, because I multiplied those together. So that's how you write the units, because those are together. So I've got G degrees C right here. This is going to be joules per gram per degree C. I just haven't written it in. Okay. Now if I move the -1 in there, can you see that I can just get rid of the negative? So I'm going to multiply the interior here of, what if I said, if you were in an algebra class and you had -1 on the outside times 4x, you could just go -4x. That's all I'm doing here. You asked me to put the times, the multiplication symbol here, but the CP is just like the x, it's just like a variable. So when I move this -1 in here, it just gets rid of that negative. You guys with me? You having fun? Your smile doesn't mean you're having fun, does it? All right, there. Now the negative is gone. Okay. What do we do now? Divide both sides by this. Now I'm going to include the units too. I'm going to divide both sides by this. So divide by this, that goes away. Grams dot degree C. So we're down to that. And that's what we're looking for, the CP of the metal. See how we do. And the negative is gone. I like that. We are going to end up in the correct units. Joules over grams degree C. Let me break those off. Joules, grams, degree C. Five. So I know if we look back at the beginning, three significant figures, 3, 4, 3. We really do only have 2 here. That happens when you do addition, subtraction sometimes. So I guess we're just keeping those. Joules per gram per degree C. That's what we get from C. This probably said try to identify the metal. I think we literally did this lab when I was at UNG, and I think we do it exactly the same way here. A lab will do it. So all this math you're actually going to do in a lab and try to identify the metal. So the one we did is this. Yay, 0.38, that's what they have. Burn. Copper is 0.385. Close to the value is for copper. All right. So if this were a lab, you'd guess copper. Our lab, you look at the metal, like steel and copper might be close to the same CP value, but they look very different, so you make a little inference on how heavy it is. Aluminum is very light compared to other metals, so you make a few other judgments on top of just the CP, and then you can identify the metal. In the lab we do. There is a check you're learning there. I'll leave that to you. Okay. I'm going to go through these last bits here, just to try not to waste too much time. Let me say this first, before I start crapping on this book. I know I'm the one that chose this book, but I kind of regret it. I like it because it's free and it's nobody had to go buy anything and nobody had to get on some website and figure stuff out. There's a few things this book does that I don't like. What I'm about to do is almost completely absent from this book. So I'll put something together that gives you kind of what do you call it? An addendum to our book. But let me show you this. If you have a reaction, and let me just in general say, So this chapter is about energy, and how energy works. So you just learned about heat capacity and how you heat things up. Notice everything we just did is all about a physical change, not a chemical change. No chemical reaction took place. Just heating something up and cooling it down or whatever doesn't change the substance itself. Now I'm going to talk about how energy works in reactions. Reactants. And just in general, let's say here's our reactants. A plus B. They go through some sort of reaction and it becomes C and D. An example might be what's up quick? LiBr becomes, when we do the switch and we get NaBr plus LiCl. Just to keep it simple. NaCl is A, LiBr is B, NaBr is C, and LiCl is D. So this is just kind of like in general. So just so I can talk about this. This didn't happen when we just heated something up like we were talking about so far all day. That was a physical change. What I'm showing here is a chemical change. Chemical change means literally a chemical reaction occurred. And the conditions for a chemical reaction to have occurred is that old bonds are broken and new bonds are formed. So the NaCl bond is broken, LiBr bond is broken, and the NaBr bond is formed, a new bond, and an LiCl bond is formed. Actually, all of these are soluble, so this is not a great example because you would necessarily be doing this in water, but assume, just to keep things simple, assume this actually happens without these being dissolved in water. Okay, and the point is, there's a certain amount of energy. So here's one thing that's not in your book. If I made a simple little graph and I said, on this axis going up, energy, and I could say joules, the same heat that we were talking about that you're familiar with that governs temperature. You put heat into something, temperature goes up. Take heat out of something, temperature goes down. So still energy. And think of this as, you could say time. You could also progress of the reaction. Meaning you have this, and then they go, and they go, and they go, and eventually everything becomes this. That's what's going on here. And you can think of it as time. The beginning of the time period here, you've got all this, and the time goes by, and then you have all this. So what I'm saying is, let's say we start here, and I say, that's the reactants. And then later we're over here, and we have products. And what I'm saying here is, there's a certain amount of energy in NaCl. There's a certain amount of energy in the LiBr. Together, if you add them together, if that's zero, that's how much energy sits inside those molecules, just sitting on a shelf, not doing anything. If you went and found these on a shelf somewhere, there's a certain amount of energy in them altogether. Here's how much energy is in those. Like if this is zero, then let's say that was 10 joules, we've got 10 joules sitting here in these. We have a reaction go, then we have this. If you didn't do the reaction, you just took these off the shelf, there's this much energy that just resides inside these molecules. And there is a difference between the two. So that's your first insight on how energy works with reactions. There is a different amount of energy at the beginning and the end. Okay. This difference in energy, the symbol for it we use is delta H, and we call it enthalpy. Don't get lost in that word, it's just a fancy word for reaction energy. It is a delta. If I calculated this, if I could find this, and let's say this was 20, and this was 10, notice, I'll say H final for the products, maybe I should say products. But you see that that's the final point. This was the beginning point, this is the final point. H final minus H reactants. Just like we did before, final minus initial. If this tall one is 20 joules, and the short one is 10 joules, 20 minus 10 is 10. What I'm saying is, instead of doing a double arrow, what happened from the beginning to the end is energy in the atoms that are there, or the molecules that are there, went up. So this is 10, for my little weird example here, delta H equals 10. You see what I'm saying? The delta H is the difference between reactants and products. The difference in energy that's in the molecules. You with me? We call it delta H, we call it enthalpy. You can call it reaction enthalpy. You might even call it reaction energy because that's really what it is. Enthalpy is just a fancy word we use here. So that picture is missing from your book. I wish it was in here. One other thing, and I'll just kind of mention it here, is really when a reaction takes place, let me get some of this clutter out of the way. I guess I can leave that there. That's the delta H. The truth is, we don't know this amount of energy, and we don't know this amount of energy. What we do is we put it in a calorimeter. We put these in a calorimeter and we measure the temperature. And then if the temperature of the, like, let's say we have here's my molecules, and I have it in this little chamber, and then I have another chamber out here that's also, this is thermodynamically sealed, that is, what do you call it, insulated. This barrier for this little chamber is not insulated, and I have the reaction go in there. I put the NaCl and the Br in there, and I let them react. I seal it up. I have a temperature in here and water, not a thermometer and water. I can measure how much heat goes into the water because I know the heat capacity of water, and I can calculate how much heat went into the water, just like we were doing before. I can find Q for the water. Then I know how much heat comes out of the reaction. Or some reactions, the product is lower. But let me stick with this for now. So you can actually measure this. So we're not measuring this and this. We're measuring the process. And if you actually measure a process like this, what you see is the energy goes up and then it comes back down. So I like to include that little detail because it exposes one other thing. And let me say again, that is delta H. The difference between products and reactants, that's the delta H. This, the difference between the reactants and this peak. This distance, it's measured in energy. We call it EA, and it's called that's called activation energy. The reaction won't go unless you give the activation energy in. And in case you're wondering, well, there's the reactants, there's the products, how the heck do you get all this energy? Well, the point is, you have to put energy into these to break them apart. That's what this is. This is breaking these apart. So it's this much energy to break these apart, and then when they come back together, this much energy comes out to form the products. I mean, from this top of the peak, is where this arrow going from that peak down to here. So it's plus this minus this is another way of getting this delta H. Do you see that? The amount of energy that goes in during the reaction minus the energy that comes out, that will also give you that delta H. Two different ways to measure delta H. I have another analogy about money and going up to the square. Let's say you're headed up to the square and I'm standing on the sidewalk and you walk by me and I go, show me all your money. And you pull out all your money, you got $20. And you go up to the square. That's me seeing how much you got. Then when you come back to the square, I'm still standing there. I'm like, show me all your money. You got $25. So I know your initial and I know your final, so I know your delta, right? Or I could stand there all innocent and let you walk by me. I could follow you around. I could watch you go in this store and buy this. And go, you're down $3 right there. And I see you go to the pawn shop and sell you your watch. $5. And I go, okay, now you're up another $5. And I just watch you spin and spin. And then when you come back, I don't need to ever talk to you. I just know you're up 3, then you're down 5, then you're up 12, then you're down this. And then when it came down to the end of it, you ended up here. So 2 different ways to measure your delta. I can measure the process, or I can measure beginning and the end. And truthfully, the process is what we measure. The process of measuring this is what we measure. We don't ever really know the absolute this and the absolute this. There are ways, but I'll kind of get there, how we can infer that, a different way to calculate delta H, or estimate delta H. Anyway, this is the basics of reaction energy enthalpy. I need to give you something that you have that looks like this. I can't believe this book doesn't have this. This is like fundamental to every energy chapter in 12 of all. My fault for choosing this book. So I'll find something that's got that in it. Okay. So there's some details there, but let me creep up on the end here and show you kind of a simple way to look at this. And something you can do with it, some calculations you can make. So yeah, we'll just erase this. And I'll end what we're doing today on something that's this straightforward plug and chug. It's even easier than what we've been doing. I told you, I have some examples. Like I said, your book didn't do a good job of this. So the last couple things I have on here, a couple pages, are from another presentation I made another semester with a book that had better examples. But this one that says 6.65, that's not in your book, but it's in the PowerPoint. Let me write this. Here's the reaction. Assume I give you this reaction. That reacts and gives us let me, before I go into this calculation, there's 4 of these, so let me draw them along. There's 4 NH3s. So I actually drew the diagram of them. And I'm showing their bonds. There's 3 O2s. These are actually double bonds, so I'll draw double bonds. And then over here, we have 2 and 2. So we have N, this is a triple bond. We have 6 H2Os, so I'll draw those. So yeah, one more conceptual detail, and then I'll show you what I think is actually a simple calculation. There's 3 ways, I suppose there's 4 ways to get delta H. One of them is to measure it, but ignore that. Think of it as being 3 different ways you can calculate delta H. I'm going to show you the simple one first, but there's what I call this. If you're given a delta H for a reaction, that's one way we're calculating it. Delta H, I'll say. There's the reaction enthalpy, what I just drew a diagram of. There's bond enthalpy that I'm not really going to get to, but I'll explain what it is. And there's one more way using, no. Yeah, there are 4 ways without measuring. Hess's law, I'll get to later. And just to give you sort of a roadmap, this is what I'm doing right now, or the calculation I'm about to show you. But I'm going to give you an idea of what estimating of delta H with bond entities are. Here's the point. You remember that activation energy I told you about? Energy got to put in just to make the reaction go. That's the energy to break these bonds. I got to break those bonds, I got to break all these bonds, and I got to break all these double bonds. It takes a certain amount of energy to do that. You can think about it like this. To make things come apart, you have to put energy in. When things come together, when these two ends come together, energy comes out. So that's that arrow that I drew up to the peak, energy going in, and then when you go down, energy coming out. Okay. And I'll get to these later. This is the calculation I want to do before we're done. This is actually conceptually easy. I didn't bring a chart for it. So you break all those bonds. That's the energy going in. New bonds form over here. That's the energy coming out. And there's two situations you can have. You can have reactants to products, and then a different reaction you can have. And the point is, here, energy goes up to here and only comes back down to here. Here, energy goes up to here and then comes back down, passes where it was, and then continues down here. In this case, that amount of energy went in. You can tell energy went in because you started here. This is me catching you on the sidewalk and seeing the money you have. I don't watch your process. You come back later, and I see that you've got more money. So you didn't lose beyond the money you had. You actually gained money while you were going out. That's called endothermic. You gained energy going from here to here. Sometimes that happens. It's endothermic. And this is exothermic. From here to here, it went down. So during the course of the reaction, energy went out. You see that? Okay. If you do a calculation and you calculate this delta H, here you will get delta H equals positive. That's what we call endothermic, because energy goes in. Here, delta H, if you calculate it, you'll get a negative value. I mean, you'll have a numerical value and there'll be a negative sign in front of it, because you literally started here and ended here. And that one's exothermic. I'm not sure whether, I can tell you whether it is. Okay, say I give you this. And I also write out here at the end, delta H equals negative 1.267 kilojoules. This negative sign tells you that we're here, that this was an exothermic reaction. If you did this reaction and you were standing near it and you held your hands toward it, you'd feel heat coming. If you had your hand around the reaction vessel, and assuming it wasn't too hot to burn you, you'd go, oh yeah, that's warm. If you did this reaction, and you put your hands around it, you feel it get cold, even though the temperature in the room is warmer than that, because it's absorbing energy. Okay. So these bonds break. Okay. In relation to this estimate the delta H, we do actually know the delta H for an N to H bond. There's a chart in the book, we'll look at it later. There's a certain value for that. There's a certain value for breaking a double bond between two oxygens. So N to H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If the N to H bonds were, let's just say, is 100, I think these are in kilojoules per mole is how they do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That means we have 1,200 kilojoules, we just do it per mole. To break those bonds, and let's say this one was 600 kilojoules to break one O to O double bond. Multiply that by 3. So 1,800 kilojoules to break those. Add the 1,200 and the 800. That's your estimate for the activation energy. See what I'm saying? You can also look up those values for N-to-N triple bond and O to H bonds, add them all up. That's the amount of energy that comes out. You just put a negative sign in front of it. So that's how you can estimate this. So I just told you how to do this now. It's really that easy. It's just that math. But we'll do that another day. But this one is very simple. So let's go back to just this. So I've given you all sort of the conceptual. That bond breaking and bond forming, I think, is worth seeing conceptually before you start doing it too easy. This is 6.65 on. Okay, but assume I give you the reaction, balanced reaction, and I tell you this, delta H. I could say, is this an endothermic or an exothermic reaction? Out of all this stuff, you only have to look right here. You know this is exothermic because energy came out. It's negative some energy. If this were positive, or the positive number, sometimes we just don't write it, then you know it was endothermic. That's one thing you could do. Okay. Earlier in the semester, assume that delta H isn't over there. I know I told you that what you're seeing here is a summary form of a bunch of different relationships. One of them is 4 moles of NH3 to 3 moles of O2. So that's that relationship. Another relationship here is 4 moles of NH3 to 2 moles of N2, and I could go on. You remember that? Once you have a delta H here, you do have all of these because you've got the balanced reaction. But now you have some more relationships. What this means is negative 67 joules to 4 moles of NH3. There's one of the relationships you have that's summarized there, now that the delta H is given. Another one. That's another relationship you have there. You see what I'm doing? And of course, there's 2 more. You just put negative 1267 for the N2 and the negative 1267 for the 6 moles of H2O. All right. Having said that, you're given this, including the delta H, and it says, what is the enthalpy change? A synonym for enthalpy change is delta H. So I could have said, what is the delta H? Let's say I do this reaction with 48.1 grams of NH. It says ammonia, but that's ammonia. I would tell you that on the test. And it's actually very simple. Well, I guess we have to do this first. We need the grams per mole. Grams of NH3 is mentioned. We're going to need grams per mole. There's 1 of those. There's 3 of those. 14.01 from the periodic table. 1.01 from the periodic table. 3.03. 7.1. So ammonia, NH3, is 17.04 grams per mole. So you do this. .1 grams. I need grams of NH3 on the bottom, which is 1704 to 1 mole NH3. And now I'm going to use this relationship. 1267 joules to 4 moles of NH3. NH3 is what we're talking about here, so that's the relationship among the four that I need. Moles on top here, so moles of NH3 on bottom. 4 moles of NH3 negative. Grams cancel, moles cancel, you'll end up in joules, that's how you calculate it. So, I know I talked a lot, but assume you're given all this, and you're asked this, that's how you calculate it. I think I pre-calculated all these. Times 10 to the 10. This is what I got. I did this another semester. So, if you're doing this reaction and you put 48.1 grams of NH3 in there, assuming you have limited this and excess this, that's how much heat will come out. You'll be able to feel that much heat come out. Can we stop there? All right. There's a few other examples here. I could go through them, but they're all done just exactly like this in practice. So the next class or two, we'll go through these other energy calculations. I pushed the test out, not to next Monday, but the next Monday. And I'll get more stuff on D2L. I did get some stuff on D2L and start practicing. I've got to get more on there, and then once I get it all on there, I'll have a test.
Thank you.
Yep.
So the test is April 6th.
Yeah, the one day.
Yeah.
Yeah.
So next Monday is April